So today what we'll be doing is we're taking a look at exponential relations. A long time ago you took a look at these things called linear graphs. So these were anything that looked like a line and followed the equation y equals mx plus b. If we had a table, we always took a look at the first differences. If the first differences were the same, then we knew it was a linear graph. When we had something that was quadratic, we knew it looked like this stuff here. Either it opened up or it opened down, but this was the basic equation that we used. Now, a long time ago in grade 10, you learned about how to actually calculate a thing called second differences. And when you got something that was a second difference, you knew it was quadratic. Now, today, we're going to take a look at a thing called exponentials. The exponential deals with a thing called a rate of growth or doubling amount. Anytime you see something that looks like y is equal to a, b to the x, we're talking about something that is either doubling or being halved in time. So let's go and write that on here. This is for doubling or being halved. Now, this last one here for our exponential thing, this one is just another version of this equation where the b has been replaced by either 1 plus r or 1 minus r, where r represents the rate, where r is the rate as a percent increase, where we add or decrease. Now, these other graphs here are just some basic ideas that you learned about a long time ago. What it means for a graph that is linear and it's increasing, right? It's growth. You can also think of linear, a slanted graph that's going from the top to the bottom as you move left to right. We consider that, you could almost call that a decay. Now, for quadratics, you kind of have a growth and a decay for both of them. But let's not talk about that. Let's focus on just this thing, the exponentials. Exponentials that follow this path here, we call exponential decay because as we move from left to right, our amount decreases as time goes on. If our amount or money or stuff that we're dealing with continues to increase over time, then we call that growth. Now, in this case, this problem here, my growth rate, my b value, my value is halved each time. That's why it's shrinking. In this part here, my value is always increasing by a multiple of 2 every time we move one step to the right. Now, let's go to our problems for the day. Now, the key concepts that we're going to look at today. What I want you to remember is this. Anytime you're dealing with exponential equations, they're all based off this one equation. Y is equal to a, b to the x. Now, the a value represents the starting value, the starting amount. And then b represents the growth or decay value. So, for example, let's say I took a look at an equation that looked like this. So let's go with the basic equation. Let's say I had y is equal to 3 raised to the x. This problem says that my starting value is 2. And every time it increases, we increase by multiplying by a factor of 3. So every time we increase or change our x value from 0 to 1 to 2 to 3, we're multiplying by some power of 3. So we're always increasing by a multiple of 3. Now, another form of this would be y is equal to, let's say I had this, y is equal to 100 times 1/2 raised to the x. Now, if you think about this, it's basically saying my starting value is 100. Now, this value here says we multiply by 1/2 each time. So in essence, this thing is decay because it's small, it's shrinking. And this one here is growth, since it is increasing. Now, let's go quickly talk about the other two forms of the equation that you might see today. If I look at this equation, I call this equation a percentage growth type problem. So this one is called the percentage growth problem, with rate R as a decimal. So let's say that I had an increase of 4% yearly with a starting value of $10,000. Or it could be 1,000 kilograms. It doesn't matter. It just depends on what our numbers are. So remember, before this was our starting value. And then this value here, our R value, I just said was the percent as a decimal. So let's look at this. 4% as a decimal is equal to 4/100, which is equal to 0.04. And I'm going to call this my R value right away. Now, the starting value is 10,000, so this is the A value in our equation right here. So when we write our equation, we end up with y is equal to, well, 10,000 times 1 plus 0.04 raised to the x. That is our basic exponential growth question. So I call this the percentage growth type problem. And you might do the same as well. So now this one here, this next one, where we have y is equal to a 1 minus r to the x. Now the minus makes you automatically think it's no longer growing. So I call this the percent decay problem. So that is where the growth rate is R in decimal. So imagine if I had a problem that described a decrease of 20%, okay, with a starting value of, say, 150 milligrams. So what you would write is this. Y is equal to, well, here we go. The start value is 150. 1 minus 0. Well, I don't know what 20% is as a decimal, so I'm actually going to calculate it. R is equal to 20%, which really means 20/100. Punch that in your calculator and you get 0.20. So we end up being 1 minus 0.20 raised to the x. And what I tend to do on my next line for this is the only one I do this for, I write this as, well, 0.8 raised to the x, because 1 minus 0.2 is 0.8. And that is a decreasing equation. And that's all we did for today. Now, what I'd like you to do is I'd like you to take a look at the problems that I've proposed for you to do, and then try to use those solutions, those problems that you see in the notes today to do the problems that I have given you for homework.